space missions will be required to collect data from far-off points in space. Others may need to point very accurately. To do this, large precision optical structures will have to be extremely steady so that the optics will have good resolution. In order to keep these structures lightweight, they end up being very flexible and tend to have a lot of structural motion. This makes it difficult to keep them in proper alignment. They require some kind of structural control. In Albuquerque, New Mexico, experiments are being conducted to advance the development of structural control for use in space. The Space Integrated Controls Experiment, or SPICE, is designed to integrate various mature technologies in a representative large flexible structure. SPICE is currently engaged in the Precision Pointing Experiment. This experiment is designed to explore the full capabilities of structural control. It will demonstrate how active and passive control techniques can be used to reduce telescope jitter by more than a factor of 100, 10 times better than has ever been done before. The structural control is brought about by a distributed control system which exerts calculated forces at many places on the structure. These forces keep the disturbances from affecting the telescope's line of sight. To accomplish this end, the emphasis is not so much on new algorithms and hardware, but rather on the careful integration of existing technologies. Lockheed Missiles and Space Company is the prime contractor on this program. The program is currently engaged in testing at a Phillips Laboratory facility located on Kirtland Air Force Base in Albuquerque, New Mexico.
The Phillips Lab is one of four principal Air Force laboratories. The Phillips Lab mission is principally to conduct research and develop technology for space applications. The Phillips Laboratory was chosen by SDIO as the agent for the SPICE program. The reason why it's here, as far as Lockheed is concerned, is because the experiment itself is being run here in a Phillips Laboratory facility, and we work very closely with the Phillips Lab personnel on the program.
Lockheed has put together a very effective team to augment its capabilities in structural control and analysis. Honeywell has great expertise in the area of control hardware and passive damping. CSA Engineering specializes in structural testing and passive damping components. In addition to these subcontractors, there are government personnel on the team who provide additional input and ideas.
We set up what is called a badgeless team, a term used by the Phillips Laboratory, in which we integrate the different contractors and the government into a single team working on the program.
The equipment in the high bay is meant to represent a large precision optical space structure, complete with a simulated segmented primary mirror and a secondary mirror. Part of the structure has a vibration source which shakes the structure. This experiment uses a number of sensors and devices to measure and control this vibration. A large part of this structure was built several years ago for the Space Active Vibration Isolation, or SAVI program, which looked at isolating one part of a spacecraft from another by the use of magnetic suspension. The structure weighs over 6,000 pounds. It is suspended by a gravity offload system, which is mounted on the roof of the building. This equipment makes it possible to hold the weight of the structure up and still allow it to move as it would in space. 6 SAVI magnetic actuators are located at the bottom of the structure to control its rigid body motion.
The equipment that's above the magnetic suspension is the precision structure we're trying to control, and unfortunately some disturbances still get through to that structure. So the next tier of the system is to try and measure the vibrations on that structure, both with optical sensors and accelerometers, and then use proof mass actuators to control those vibrations and attenuate them by roughly a factor of 100.
18 proof mass actuators, manufactured by Harris Corporation, will provide the control authority. These devices will be distributed on the tripod legs and outer extents of the lower bulkhead. Accelerometers are co-located at the proof mass actuators.
The proof mass actuators are the actuators we use to bring about our control system. They're crucial to what we do. Proof mass actuators are sources of inertial force. There's nothing in space to push against, so we have to somehow pull out of our hat a force to push against the structure in order to do our structural control. This is a proof mass actuator. Inside is a heavy proof mass which can be moved by electronic command and which causes a reaction force on the housing and thus onto the telescope structure. The proof mass is suspended between two springs, two flexure springs, one of which you can see at the end here. The motion is very small, only about 6 millimeters, but that's enough to cause a 40 Newton reaction force against the structure.
An optical sensing system has been installed on the structure to measure optical performance parameters with great accuracy. The accuracy required of such measurements, extremely difficult to achieve within the Earth's atmosphere, is better than 1 microradian. All the measurements that are made on the structure, both from the optical devices and from the accelerometers, are fed back through the interface electronics into a very fast computer. The computer determines which forces the proof mass actuators should apply in order to minimize the vibrations in the telescope's line of sight.
Every 1 millisecond, which is 1,000 times per second, the accelerometers, of which there are 18, and the 18 optical measurements from the optical sensing system, those sensors are all sampled. And that data then is transmitted to the STAR VP3 array processor. The array processor does a single matrix multiply, which is a 186 by 222 matrix multiply. That single matrix multiply includes the entire control system algorithm in it. All of those inputs, the 36 inputs from the sensors, are processed, and the outputs are the 18 commands to the actuators. Lockheed is very closely teamed with the Air Force in developing the model of the structure. The model of the structure is what I used to develop the control system.
In addition to helping with the development of the control system, accurate modeling is essential to prove the success of the experiment. The SPICE program has achieved an unprecedented correlation between its models and its hardware. The first 30 modes agree to better than 10%.
The Air Force's job is to monitor the contractor and to also provide input and ideas as to another way they could model the structure. Lockheed has their model, we have our model, and we try to get to the same answer using different approaches.
All the elements of the SPICE precision pointing experiment are being tested. The optical scoring system, the control system, the proof mass actuators, and all the interface electronics must be integrated properly. The results of the experiments performed on the SPICE testbed will show the vibration suppression capabilities of several passive, active, and combined passive and active techniques.
We're getting started in the open loop tests as part of the SPICE precision pointing experiment. And in particular, we're looking at some of the optical scoring system sensors integrated into the SPICE structure. And those sensors are part of the feedback group of sensors to tell us how well the control system is performing.
The SPICE technology could be applied to a number of space-based structures, which are required to be able to point with great precision. A very quiet platform is essential for this task. The SPICE program is demonstrating that structural vibrations can be controlled to achieve this accurate pointing in space.